In this video, I talk about unconstrained minimization in the context of fitting a model to noisy data. The video is based on the example script example_minung_2. Again, we start in line 3 with the usual preamble. We set various defaults, close all windows, we set the format specification, and we will demonstrate both minimizers we have encountered in the last video, namely fminsearch and fminung. Now let's first generate the problem. We define a vector of x values in the variable x. The vector xx is only for plotting, and we define a logarithmic model which tells us the observation is k times the log of x plus a constant d. And we assign values to k and d. We compute the model on our vector x and also for plotting on the vector xx, and this is the model which we are going to use in the following. So the model is represented by the green line. The true values of the observations are represented by the green circles. And now we're going to add some noise, Gaussian noise, to these true values of y, and then fit the model to the noisy data, which means we estimate k and d, the constants k and d, from the observations. To this end, we have first to choose a random number generator. It's a default one. We set the random number sequence to the default start value. We define some colors for plotting, and we set the standard deviation of the Gaussian noise we are going to use. So first we add Gaussian noise to the values in y, and we get yn, where n stands for noisy. This is accomplished by the function norm rnd, which generates normal random numbers or Gaussian random numbers centered on y with the standard deviation sig, which is 1 in our case. So let's immediately plot the noisy data. These are the green plus signs. And now we proceed to estimate k and d, the model parameters k and d, from the noisy observations. This loop steps over the two minimizers fminsearch and fminung. We start with minimization with fminsearch. Now, which is the function to be minimized? This function is called mydist, my distance. The starting values are the true values in this case. And the function we minimize is called mydist. This depends on the model parameters k and d. So par is a vector of two variables, k and d. It depends on the x values, on the observations, and it also depends on the model, which is called mymod in line 23. Now let's have a look at the distance. This distance is a measure of the discrepancy between the model and the observations. So in this function, we have the parameters of the model as the input. This has to be a vector if it is to be passed to a minimizer. It depends on the x values, the y values, and the model. First, I check the input, then I check that x and y have the same length. Then I unpack the model parameters k and d from the parameter vector par. I compute the model, and then I compute the discrepancy between the observations y and the model values y mod. In this case, this is the sum of the absolute differences between the observations, which are in y, and the model values, which are in y mod. Let's put a breakpoint here so that we can see this function in action as soon as we call the minimizer. So the starting values are the true values. The options are set in line 50, and the output are the estimated parameters k and d and the distance that remains between the observations and the model. Distance meaning sum of absolute differences, or L1 norm. So let's execute the minimizer, and we will stop immediately in the distance function in line 81. Okay, so let's do these checks. These are of course okay. Par now contains the current values of k and d. We unpack them, we compute the model values, and we compute the difference between the model and the observations. The observations are in y, the model values are in y mod, and d is the distance, which is rather large at the beginning, 25 point something. We'll see that it decreases during the minimization procedure. Let's continue. So these are the new values of the parameters found by fmin search, and this should give a smaller distance than before. Yeah, it's slightly smaller, and so on. Now let's stop at line 52 and complete the minimization. Okay, so what are the final estimated values of K1 and D1? This is K1 and this is D1. I recall the true values were 2 and 5. Now let us plot the fitted model, fitted with fmin search. So the red line is now the fitted model, fitted with fmin search. The red diamonds are the model values of this model at the points in X. And we also display the final value of the objective function. It's 22 point something. So it has decreased from 25 point something to 22 point something. This terminates the optimization or the fit by fmin search. Now let's do a similar procedure with fminunc. So now we minimize with fminunc. You see that the final value of the objective function is slightly larger with fminunc than with fmin search. Also, the model parameters are quite different, and we see in the figure 1 that the two models are not the same. They are similar but not the same. So the red line is the fit with fmin search and the blue line is the fit with fminunc. I recall that distance function is the sum of the absolute differences between observations and model values, and in this case this objective function, this distance function, is not differentiable everywhere, so this probably explains the difference between fmin search and fminunc. Let's have a look at a different model, the same model but different data. We regenerate the observations. So we now use a different set of random numbers, giving us a different set of observations. And of course, the fitted models will be different from the previous iteration. Okay, in this case, the two fits are very similar, although not identical. Let's have a look with a couple of more examples. In this example, the fits are almost identical. You see in the command window that the final value of the objective function of the distance function is nearly the same, very small difference. They are quite different here. Again, quite different also here. Here they are more similar. And here they are virtually identical. How to distinguish the two fits? This terminates this video. The next video will be concerned with the problem of global optimization or global minimization, presenting two algorithms for finding a global minimum, not a local one, but the minimum which has a smaller function value than all the other ones.